my final career interest presentation on extragalactic astronomy, specializing in galaxy formation and evolution. As recently as the 1920s, astronomers thought that galaxies were in fact spiral nebulas, or disk-shaped clouds of gas and dust within our own galaxy, the Milky Way. But in the late 1920s, an astronomer named Edwin Hubble, using what's called a standard candle, or object that's always the same brightness at a given distance, that these spiral nebulas were in fact separate galaxies or separate disks of gas and dust that were on the order of millions to billions of light years away. Our Milky Way is only about 100,000 light years across. The Andromeda Nebula, as it was once called, now known as the Andromeda Galaxy, is something like 2.5 million light years away, and that's the closest one we know of. Our current understanding of physics tells us that objects closer to a center of mass should rotate or orbit faster than objects further from the center of mass. Think of our solar system. The inner planets go around in a matter of months. The outer planets take hundreds of years. Vera Rubin found, by looking at the Andromeda Galaxy, that the intersections of the galaxy are traveling at about the same rate as the outskirts, or outer spiral arms, of this galaxy. This meant that there had to be invisible matter on the outside of the galaxy that was pulling on the outer regions to make it behave this way. Either that, or our current understanding of physics is slightly wrong. Either way, the implications are enormous for our understanding of the universe. We currently call this dark matter, and along with dark energy, it makes up more than 90% of the known universe, and nobody knows what dark matter or dark energy are. This is a radio image of a distant galaxy with giant jets emanating from the accretion of matter around a large black hole in its center. Black holes are collapsed stars that are so dense that nothing, not even light, can escape their gravitational pull. Supermassive black holes can contain the mass of something like a few million suns. One of the biggest mysteries in astronomy is why so many galaxies contain these so-called supermassive black holes in their cores, and how these are linked to their formation and growth over time. This projection from the 2-micron all-sky survey shows the general distribution of galaxies throughout space. You can see there are large voids between these ribbons or sheets that contain the galaxies, and they're generally distributed like soap bubbles in space. Now, we know that galaxies are moving away from one another. We've known this for a while, but we also know that they are accelerating in their expansion. And this was discovered only recently by discovering that when we plotted the movement of galaxies, the universe is acting like it had a negative mass. And the only way this is possible is if the expansion of the universe wasn't slowing down as expected, but it's actually speeding up. The agent of this expansion, known as dark energy, is essentially a small repulsive force throughout all of empty space that can build up over light years and push the stars and galaxies apart. This image is a cutaway of the planned Large Synoptic Survey Telescope, which is going to have a huge field of view of about 10 square degrees and will image the entire sky every few nights. This will allow us to see large-scale changes across the night sky, including near-Earth objects like asteroids, but also the movement and interaction of distant galaxies. Astronomers use a variety of wavelengths, including optical, X-ray, gamma ray, infrared, and radio, to observe the night sky, depending on what they're trying to see. Usually shorter wavelengths are useful for high-energy events in deep space, whereas longer wavelengths, like radio, are good for peering into clouds of dust and gas and the center of our galaxy, which is normally obscured at visible wavelengths. This is the control room at the 4-meter telescope on Kitt Peak in Arizona. To get time on a big research telescope like this, you need to be an established research astronomer with a track record of attracting grant money and publishing research papers. To do this, you have to first acquire a PhD in astronomy, usually be appointed to a postdoctoral research position, and working your way up from there. There is a limited amount of grant money and it is extremely competitive, so good proposal writing skills are key, and being an effective communicator is extremely important. This here is a picture of M63, the sunflower galaxy, that I actually took using a CCD camera on a 20-inch research grade telescope. So the most recent salary outlook per year is about $100,000. The top employers for astronomers were the government, research and development services, and then universities. The projected growth of the profession is about 7%, which is about the same as all of the jobs combined. It's not lagging, but it's also not ahead of the pack either. And it's expected to get more competitive because a lot of PhDs are currently graduating and entering into the field. If one doesn't make it in astronomy, there are other options, such as computer science positions, science, technology, engineering, math, education and outreach, and technical jobs like operating telescopes or other similar jobs. Thanks for watching. If you're interested in any of these topics and want to learn more, you can check out the bibliography at the end of the presentation, and clear skies.